Okay, in this video, we're just going to discuss what we mean by the boundary of a region in space that's enclosed to be oriented in the same way as the surface. So we want, in terms of orientation, this is how we can think about it, that if you imagine walking along, so if you were to walk along the boundary of your surface S, with your head pointing in the direction of the normal that you've already specified, right? So head in direction of the normal, how the normals are pointing on your surface. Then your left arm, as you walk along, should be over the surface or pointing into the surface. Why do we want this? Well, remember, if we look down here at Stokes' theorem, I just made a quick statement of it here. Remember that we have a global circulation around the curve. The boundary of a surface is measured by a localized curl of what's happening on the inside. We want those to be in the same direction, right? So let's take, for example, the half hemisphere that I've drawn here. This is a surface that has a boundary, and its boundary is the curve down here. The circle is the boundary of my surface. So in this case, the boundary is the rim of the base of that hemisphere. I'm looking at this first example. This is the boundary. If we had an entire sphere, it would have no boundary. And so Stokes' theorem could be applied, but the result might be surprising. You could think of it as slicing the sphere in half and then considering one boundary going oriented in one direction, the other boundary oriented in the other direction. When you measure circulation, they will cancel out. So we're interested in surfaces that have boundaries. The second bottle-looking like thing, I don't know, cornucopia, has a boundary that is also a circle right here. And this one has a boundary that's this curve, maybe an ellipse, right? So all of these have boundaries, and they're closed curves, and then enclose a region. And so we want to think about how we might orient our curve so that it's in a consistent orientation with the normals, because we want to measure curl in the same direction as we're measuring the circulation on the outside of the over the boundary. So let's imagine with the first one that we are walking along the hemisphere, along the boundary of the hemisphere. Maybe I'm walking over here on the other side, and my head is pointing up in the direction of the normal. I want my left arm to point to the surface, which means that if I want to do that, my left arm to point to the surface, I should be walking in this direction. So in this case, we would orient this, this would be called a positive orientation, or orientation compatible with the orientation of the normal of the surface. If we take a look at the cornucopia thing, let's call this one just so I can refer to it. Let's look at this one. So I already explained that the boundary is this piece, this kind of opening. The curve around the opening is our boundary. And I want to figure out, how do we orient this if my normals are pointing outward in that direction? So once again, you imagine yourself walking along the rim, walking along the edge, and thinking, okay, which way would I walk? I can either walk up that way or down this way. And I need to do it if my head has to point to the normals, and when I'm walking, I want my left arm to point into my surface, over the surface, then in this case, we want to walk in this direction. Because if we walk in this direction, right, then you can think, okay, I'm facing this way, my left arm should be pointing towards the region. If I'm going the other way, then my right arm will point over the region. So that's how we think about our orientation, so that the curl on the surface is oriented in the same direction as the circulation on the boundary, how we're measuring the circulation on the boundary. I don't know if in that case then it would be this way. Okay, Let's look at our final one where the normals are pointing down. And I've drawn a little person already. The head is pointing down along the normals, and I want to figure out how do I walk around this so that the region is to the left. So my arm points to the left. So do I want to walk this way or do I want to walk this way? Well, if we walk, and remember we're upside down, so if we walk that way, I believe that my right arm will be over the curve, the surface, I mean the region. This is my region. That's the surface. If I walk this way, because remember we're upside down, then I can imagine that my left arm, let me just make sure. This one's always hard for me. Then my left arm will point into the surface. So we want to orient our curve so that it's going in what we see now as the clockwise direction, right? But in space, it's hard to determine clockwise and counterclockwise. So this is what it means to orient our boundary incompatibly with the normal. Now it depends, you may choose a normal that points inward into your surface and then you orient your curve that's compatible with that. If it points outward, you orient your curve that's compatible with that so that the left and right side of our equations can be equal to each other. If we orient in a way that's not compatible, you're just going to be off by a negative sign in your final answer.